Hi everyone, I am T. Vishnu Sagar from CSMC, SRT. Today I will explain about the topic preparation, properties and applications of nylon and bakelite. Nylon and bakelite is a tale of two polymers, the two revolutionary materials that transform modern manufacturing and everyday life. From the laboratory to our pockets, discover the chemistry and legacy of the polymers that changed everything. Our journey exploring revolutionary polymers. First one, origins and discovery. Understanding when and why these materials are invented and the revolutionary scientists behind them. Second one, chemical synthesis. Exploring the precise molecular processes that create these polymers from raw chemical precursors. Third one, physical properties. Examining the unique characteristics that make each material distinct and valuable for specific applications. Fourth one, real world applications. Discovering the countless products and industries that depend on nylon and bakelite today. Nylon, from humble beginnings to everyday essential. A synthetic revolution. Nylon was first synthesized in 1935 by Wallace Carruthers at DuPont, marking a watershed movement in polymer chemistry. Originally developed as a synthetic alternative to silk for use in parachutes and military applications during World War II, nylon quickly became indispensable. The material's remarkable strength, flexibility, and durability made it deal for stocking, which created an enormous civilian demand. Today, nylon remains one of the most widely used synthetic polymers globally, found in everything from clothing to automotive parts to industrial equipment. The chemistry of nylon. Polyamide synthesis. Nylon is a polyamide synthesized through condensation polymerization reaction. The most common form, nylon 66, is created by reacting with adipic acid and hexamethylene under controlled conditions. This reaction forms strong amide linkages C double bond O bonded to NH between molecular chains, which provide nylon's characteristics, strength, and resilience. Monomers. Adipic acid and hexamethylene combine to form the basic building blocks of nylon 6,6. Condensation. Water molecules are released as the monomers bond together, forming long polymer chains through repeated amide linkages. Chain growth. Polymerization continues until extremely long macromolecular are formed, creating the fiber structure and mechanical properties of nylon. Properties of nylon: strength, versatility, and beyond. Nylon possesses an exceptional combination of properties that make it invaluable across industries. In high tensile strength allow it to withstand significant mechanical stress, while its flexibility prevents brittleness. The material exhibits outstanding abrasion resistance, maintaining integrity under repeated friction. Nylon is lightweight compared to metals, yet durable enough for demanding applications. It also demonstrates excellent chemical resistance to oils, greases, and many solvents, and it can be easily molded into various shapes when heated. It has tensile, it has flexibility, chemical resistance, and lightweight. These are the properties of nylon. Bakelite, the dawn of the plastic age, pioneering the plastic revolution. Bakelite, it was created by Leo Baekeland in 1907. It was the world's first fully synthetic plastic and revolutionized manufacturing. Unlike natural materials such as rubber and cellulose, bakelite was entirely man-made from phenol and formaldehyde. Simple, abundant chemicals. Its introduction transformed everything from electrical components to consumer goods. Bakelite became the material of choice for radio housings, telephone pots, and countless electrical applications. Through never plastics have largely replaced it today. Bakelite remains historically significant as a material that launched the modern plastics industry and changed how are manufactured everyday objects. The chemistry of bakelite. Bakelite is formed through the condensation polymerization of phenol and formaldehyde. This reaction creates a rigid cross-linked polymer network called a phenol formaldehyde resin. Unlike linear polymers such as nylon, bakelite features extensive three-dimensional cross-linking which accounts for its hardness and heat resistance. The reaction is typically catalyzed by acid or base and proceeds in stages, allowing manufacturers to control the degree of polymerization and final material properties. Starting materials phenol and formaldehyde are inexpensive, readily available raw materials derived from coal tar and natural gases. Cross linking extensive three dimensional bonding between polymer chains creates a rigid thermostatic matrix that cannot be remelted. Heat treatment heating accurately and completes polymerization, enabling final shaping and curing of the material. Properties of bakelite it has durability and electrical insulations. Bakelite's rigid cross linked structure imparts remarkable durability and heat resistance. The material remains stable at temperatures up to 300 degrees Celsius and it does not soften or deform like thermoplastic polymers. Its exceptional electrical insulating properties made it the premier choice for early electronics. It prevents electrical current flow through withstanding high voltages without breakdown. Bakelite is also highly resistant to moisture, chemical attack, and mechanical wear. However, as a thermosetting plastic, it can be remelted or reformed once cured, and it becomes brittle over extended time periods as the polymer structure degrades. And the temperature tolerance is at 300 degrees Celsius. Electrical insulation is 99 degrees Celsius. Chemical resistance is very high. Diverse applications where nylon and bakelite shine. Both materials have become embedded in virtually every aspect of modern life, serving distinct niches based on their unique properties. Their successful applications demonstrate how molecular chemistry translates into practical solutions for real world challenges. Nylon applications. It is used in the textile and industrial purposes. It is used for the consumer and aerospace purposes. In textiles, clothing, stocking, and hosiery. And in industries, automotive parts, bearing, and gears. For consumer purposes, fishing line, rope, and sporting equipment. Aerospace, parachutes, and aircraft components. Backlight applications. Electronics, early radios, telephone housings, and electrical insulators. Decorative purposes, buttons, jewelry, and collectible items. And in industrial purposes, circuit breaker components and high voltage insulators. Legacy, still used in specialized electrical applications. Scientific innovations, both nylon and bakelite represent breakthrough achievements in polymer chemistry, demonstrating humanity's ability to engineer new materials from fundamental chemical properties. Contrasting designs. Nylon's linear structure provides flexibility and strength. Bakelite's cross-linked matrix delivers rigidity and heat resistance. Their difference illustrate how molecular architecture determines material properties. Lasting legacy. Through developed over a century ago, these polymers remain commercially significant, with nylon thriving in modern applications and bakelite persisting in specialized contexts. Foundation for the future. Nylon and bakelite paved the way for today's advanced polymer engineering, from high performance composites to biodegradable materials, sh- shaping the materials science landscapes. Thank you.